Thank you, viewers. Welcome again to this lesson. And today we want to look at structures of covalent bonds. Earlier, in our previous lesson, we talked about covalent bonds and how to use a dot cross diagram to be able to represent these covalent bonds. We also talked about dative covalent bonds, which we were able to give examples about ammonium ion, hydrozonium ion, and also aluminium chloride dimer. Now, today we want to look at the structures of covalent bonds. We know that in ionic bonds, we say this structure in ionic bonds is called giant ionic structures. But in this case, in covalent bonds, as you can see, I've indicated there are two types of structures here. There's what we call the simple molecular structure and the giant covalent or giant atomic structures. Remember that all these structures have covalent bonds in them, all of them. But now the question comes where we come to the number of atoms involved in that compound. So today we want to look at simple molecular structures. And I want to explain what simple molecular structure is. When we talk about simple molecule, the word simple here, we can really interpret it to mean few atoms. So we are talking about a molecule, a covalent compound, a substance which is covalently bonded with very few atoms in it. Could be 2, 3, 4, 5, could even be 30, but that 30 we are still considering at very small. For example, if I take sugar, C6H12O6, this is glucose. If you look at the number of atoms involved here are 12 plus 12, which is 24. So that 24 we still consider this very simple molecular structure, not giant. Giant, we are talking about millions and millions of atoms coming together. So it means therefore that in simple molecular structure we talk about simple things like water with 3 atoms only. We talk about carbon dioxide, we talk about chlorine, we talk about sulfur. We know sulfur as sulfur 8. It has 8 atoms. So that is still considered as a simple molecule. So when you talk about simple molecular structure, we are talking about substances or compounds that are having very few atoms in them. And I said that very few should just be few in the number like few, 1 or 2 or 3. It could mean 30 atoms, 20 atoms, 24 like we have seen in sugar. It's still just referred to as simple. Now, this simple molecular structure, there's something unique in them than any other structure we're going to see. That in simple molecular structure, we have 2 types of forces. The 2 types of forces we have in simple molecular structure, number 1 is intramolecular forces, molecular forces of attraction. And intramolecular forces of attraction, if I explain what this one means, is that the forces of attraction within a molecule. For example, in this case, if I talk about carbon dioxide, I'll say the compound is this one, if I draw the displayed formula. So the intramolecular forces are this one, the covalent bonds holding the atoms. So in other words, intramolecular forces of attraction hold the atoms together. And in this case, these intramolecular forces of attraction, we say that they are covalent bonds, whether in sugar, whether in iodine, whether in water, whether in whatever. They are covalent bonds. And these forces of attraction are very strong. So these atoms are very strongly held together by covalent bonds, which we have said are generally referred to as intramolecular forces, the force of attraction within a molecule, within one molecule. And I said those forces of attraction hold the atoms together. The other force we have here is intermolecular forces of attraction. Intermolecular forces of attraction, these are forces of attraction that hold the molecules together. We know here we have a molecule, one molecule here, CO2. But this CO2 can be connected to another CO2, can be connected to another CO2, can be connected to another CO2. The forces of attraction holding these molecules together, this is what we call intermolecular forces of attraction. So we know that in intermolecular, simple molecular structures, you have to really identify 2 forces. One holding the atoms together to form a molecule, then another holding the molecules together. Now in this case, we have one molecule only. Within it, we have covalent bonds, which are the intramolecular forces. And then after a molecule is formed, the molecule is attached to another molecule, is held to another molecule, which is now what we call the intermolecular forces of attraction. Now we are going to talk about two main intermolecular forces. One of them is the van der Waals forces. Van der Waals forces. The van der Waals forces are also here. These are van der Waals forces holding carbon dioxide. Then we talk about hydrogen bonding. Hydrogen bonding, hydrogen bonds. Now, these are the two intermolecular forces we are going to talk about. We are not going to see all of them everywhere. I'm going to mention a few substances with hydrogen bonds. But when it comes to van der Waals forces, they are almost, majority of the molecules have them. For example, if we talk about this carbon dioxide sulfur 8, we are talking about van der Waals forces. Hydrogen bonds exist in substances like ammonia as hydrogen bond. We have water as hydrogen bond. We have hydrogen chloride as hydrogen bond, hydrogen fluoride as hydrogen bond. Those are cases where we have hydrogen bond. And you realize that those substances with hydrogen bond, they can dissolve in water. That's the funny thing with these things. Those molecules with hydrogen bond usually dissolve in water. That's why if you dissolve hydrogen fluoride in water, it forms hydrofluoric acid and hydrofluorous acid. You dissolve this in water, it forms for you hydrochloric acid. You dissolve ammonia in water, it gives you ammonium hydroxide. So we are going to see that those with purely van der Waals forces never dissolve in water completely. But those ones that have hydrogen bonds will dissolve in water. And you are going to see that happening every day. Now, I've explained that there are two types of weak intermolecular forces here. Remember that compared to ionic bonds, these forces are very weak. That is why the substances with simple molecular structures are very low melting and boiling point, and sometimes they are mostly gases at room temperature. For example, we talk about hydrogen chloride, hydrogen fluoride, we talk about ammonia, we talk about chlorine, we talk about oxygen, we talk about carbon dioxide. They are gases at room temperature because they have very weak forces of attraction. The weak force of attraction holding the molecules together, which can be easily broken by using very little amount of heat energy. Now, we also know that even though we say they are very weak, some of these, when we compare this category, for example, we know that sugar is solid, iodine is also solid, water here is a liquid, carbon dioxide is a gas, chlorine is a gas, sulfur 8, this sulfur here is also solid. Now, why are some solid, some liquid, some gases? Some are solid, some are gases for two reasons. One, hydrogen bond is known to be very strong compared to weak van der Waals forces. So it means that water, for example, with a strong hydrogen bond is held, the molecules are much more pulled closer to each other by strong hydrogen bond, and we know that hydrogen bonds, I've said, is stronger than van der Waals forces. So we expect that carbon dioxide gas with van der Waals forces will be a gas, but water with hydrogen here is a liquid due to the strength, the variation in the strength of these bonds here. But another factor that will affect the strength of the melting point or the force of attraction holding these molecules together would be the molecular mass. The relative molecular mass of these items here will also cause a change. For example, small molecules are very weak forces. For example, if I talk about ammonia, the molar mass of ammonia is just 17. That is, nitrogen is 14 plus 3, 17. But I talk about something like carbon dioxide, which is 44. That is carbon, CO2. Carbon is 12 plus 16 times 2, that's 32 plus 12, that's 44. If, without even looking at it, if we compare the melting point or boiling point of ammonia and hydrogen, carbon dioxide, we expect carbon dioxide to have a higher melting point and boiling point because it has got, there's something that affects the weak van der Waals forces. The bigger the molecule, the stronger the van der Waals forces. So we know that this one, the van der Waals forces in the carbon dioxide is stronger than the van der Waals forces in ammonia or hydrogen bond in ammonia. So we expect this one to be having a higher melting point than this. And if you look at, this is the true thing we are going to see. If you look at sugar compared to carbon dioxide, sugar is C6H12O6. We expect sugar to be bigger. If you get the molar mass of sugar is around 180. 180, if you compare mass of 144, you really see that even sugar is solid at room temperature. That's a reason enough. This room solid, this is a gas. So we expect this one is a solid because the strength of the van der Waals forces holding these atoms, holding these molecules together in sugar is very much more stronger. And I've explained that strength increases due to the increase in molecular masses. The bigger the molecule, the stronger the force of attraction holding them. We have said we can only compare those substances in their group, that is simple molecular structure. And I said even if we say they are weak or low melting point or boiling points, but the question is those melting and boiling points also vary from one compound to another. And I said they vary based on molecular masses. The bigger the molecule, the stronger the forces of attraction in it, and therefore the higher the melting point and boiling point. But I've also pointed out that if you have a compound with both hydrogen and another one has weak van der Waals forces, you expect hydrogen bond to be the one that is strong. And I've explained that is why you can be asked why water is a liquid at room temperature and carbon dioxide is a gas. If you try to look at what I've explained here based on molecular masses, you will be surprised. We expect carbon dioxide to be a mass of 44, like I have explained, but water to be 18. So you realize that if you are using this argument here, it won't work out, because you will try to say that carbon dioxide should have a higher melting point because it has a bigger mass. And I said that this one influences, but this is not true. This is not true because water has hydrogen bonds, and I said hydrogen bond is much more stronger. So therefore, water is a liquid at room temperature, meaning we require more heat energy to overcome the force of attraction holding water molecules than we require to overcome the forces holding the molecules of carbon dioxide gas. So these are some of the things you need to develop in your mind. How do you compare these things? And I want you to take keen note of the things I've mentioned here. This is where you are going to get the idea. So all the other structures we are going to talk about, the giant covalent structure, there's no intermolecular force. Ionic bond, there was no intermolecular force. Metallic bond, there will be no intermolecular force. The only way we have intermolecular forces is simple molecular structure, because we have to develop things in two steps. One step is form a molecule first, and within that molecule there are forces of attraction called intramolecular force. In this case I've said covalent bonds. After forming the molecule, connect one molecule to another molecule. The forces holding one molecule to another molecule, we call them intermolecular forces. And in this case I've said we have mainly two types, the van der Waals forces and hydrogen bonds. I've mentioned some of the things with hydrogen bonds here. And I said that when it comes to solubility, those molecules with van der Waals forces will not dissolve in water, but those ones with hydrogen bond will dissolve in water. And you can bear me witness that if you bubble ammonia in water, and we explained in the previous lesson that ammonia dissolved in water forms ammonium hydroxide, water, hydrogen chloride will dissolve in water, hydrogen fluoride will also dissolve in water. Now what about when you talk about melting point? I've said melting point is very low. Melting point of intermolecular substances, simple molecular substances, are very low because the weak forces of attraction, the weak intermolecular force of attraction require very less heat to overcome. That is one thing. What about, but we have also said that these melting points will increase from one molecule to another based on the molecular masses. The bigger, especially weak van der Waals forces, the bigger the molecule, the stronger the van der Waals forces holding the molecules together. That is why I've explained that sugar is a solid at room temperature, while carbon dioxide is a gas. For example, if you look at chlorine, group 7, iodine, chlorine, we talk about fluorine, and so on, you realize that iodine is a solid while this is a gas. Why? Because the bigger the molecule, the higher the melting point. What about electrical conductivity? These substances don't conduct electricity completely. Why do they not conduct electricity? They don't conduct electricity because we know in chemistry we have two particles that can conduct electricity. One of them is delocalized electrons. Delocalized electrons. So they lack this delocalized electron. There's no delocalized electrons because, as we explained before, the compounds share electrons. These electrons shared here are fixed in a position that they cannot move, so they cannot be free to carry electric charge. The other thing they don't have is ions. They are not ionic compounds. The ions are absent. So the reason why they don't conduct electricity is because they don't have the localized electrons. They also do not have free or mobile ions to carry electric charge.